Morning, everybody, and welcome to session two. This is our research sprint with a focus on Ireland 2050, our innovative energy future. So as a country, we really set ourselves a big challenge in terms of transitioning to a climate resilient, biodiversity, rich, environmentally sustainable and climate neutral economy by 2050. And I suppose the big question is, how are we going to reach that? How are we going to meet this challenge? And I suppose we'll need a diverse range of technologies to decarbonize our energy system, and we'll need to act collectively to increase the rate of our decarbonisation of various sectors of the economy. So as a country, Ireland is very lucky that we do have a lot of natural resources, and we have lots of talented people that can constructively use these natural resources. And today we are going to be talking to lots of talented experts that are going to share their work with us. And, you know, I'm excited to hear from each of you. And this is a research sprint, so it's going to be a bit of a challenge because each person will have a maximum of 7 minutes. But I know that each of you are up to that challenge, and I'll have to play bad cop and come in and let you know about a minute before your 7 minutes are up. So the first person I'd like to welcome is Virkam Pakrashi. So Virkam, if you'd like to introduce yourself and tell us about your presentation, please.
Thank you. So I'm Virkam Pakrashi, and I am the Director of Dynamical Systems and Risk Lab. I run the UCD Centre for Mechanics. One of the important things that we have in Ireland for these kind of work is we need enough number of reference projects which show how a certain thing can be done. So in this case, I'm going to present the project Remote Wind, through which RDD 613, we carried out a wind turbine monitoring of an operational wind farm in Ireland. And that's the Bord-na-Móna wind farm that we worked on. And here's a quick whirlwind tour of how these things were done. I do see that the image is slightly off here. I don't know why, but maybe it's coming on fine on your side. We are looking into Bord-na-Móna wind farm, and this is a wind farm. I'm not going to read the whole slide, of course, but it's coming to the end of its lifetime. And as we start working with it, we'd like to know how much is it degrading over time? Is it working fine towards the end of its lifetime? And what kind of technologies are available to work with them? To that extent, one of the things that we worked on was multi-point scanning laser Doppler vibrometer, where you can just put the Doppler vibrometer away from the turbine, perfectly non-contact. There's very little interaction with the turbine. You don't need to access it, so it's very safe, and get the vibrations. We also took monitoring from the inside of the tower with wireless accelerometers and on the nacelle. Why? Because vibrations and movements and responses from a turbine, that links back to fundamentally its stiffness, and the stiffness is links back to its health. Because if something gets weaker, it gets less stiff. And also if the boundaries, if they start giving, you'll see that changing in the turbines. What's important with these wireless multi-point Doppler vibrometries, and we actually have the only one right now here, is you can monitor many points at one go, and you can get the live response of its modal properties, of its natural frequencies, of its mode shapes, so on and so forth. That's actually very, very important and interesting to find out rapidly what's going on. Here's an example of us focusing directly close to the nacelle, and you can see that live we're getting from all these points what's going on with the turbine very rapidly. That's very important. Similarly, we put wireless accelerometers all inside the turbine and be excited with the ambient vibration, which is the wind, but also with, you can see this massive hammer. So these sledgehammers input controlled impulses to the tower without damaging anything, and we get both the inputs and the outputs. Then through various analysis and frequency responses, we find out some of the consistent peaks, which are then representative, they're markers of the health of the tower. Similarly, after that, we carried out drone-based blade inspection because, as you know, edge erosion, that's linked to the performance of wind turbines, and also thermal imaging, which gives rise to the analysis of, okay, can we find out unknown cracks and everything. So the good news is, of course, not of course, but the good news is they are doing fine pretty much. Subsequently, we carried out lots of assessments which require some amount of contact or some amount of breakage in the whole system. To do that, we dug up the entire foundation of the wind farm, and we used GPRs, ground penetrating radars, and other techniques, for example, scanners, to find out what is the condition of the reinforcement inside. What is the condition of corrosion? How far has it degraded? Along with chemical analysis and strengths. So the cover is fine, the strengths are doing fine, and it has been taken good care of. There is some onset of corrosion, but it's also at the end of its life, so it's fine. What happens after this right now? So we have started long-term monitoring of these towers. Here's an example where monitoring of the foundation underneath and also in the tower. It's very unique. We have started that for a very long time. We're talking about more than a year that we're going to do it for now. And that will give us a lot of insight into how wind turbines behave, what their health is, and what we can do in future to implement this all over the country. So this is a national reference project, and I'm very happy to have been leading it. Thank you.
You went under time, so congratulations.
And maybe I can take one or two questions. Meanwhile, that's why I thought, like, because it's the very first example of that kind of monitoring in Ireland.
We'll actually do a whole set of questions after the first couple of talks. So we'll come back to you, Vikram, if we have any questions. And I would encourage people to put questions in and let us know if you do have.
No, that is perfect because we were supposed to start at 10:03. It's 10:10, so we're back on time. Thank you.
You did a perfect job. Well done, Vikram. Thank you. And now I'd like to welcome Divyanshu Sood. And if you can introduce yourself and tell us a bit about your presentation.
Yeah. So hi everyone. I hope you can hear me clearly. So my name is Divyanshu, and I am a PhD student in the School of Mechanical Engineering at UCD. So I am working with James O'Donnell in his laboratory building information modeling. So yeah, today I will be talking about the project which I am a part of as a PhD student. The project is ALIVE, which is assessing the indoor environmental quality IEQ and energy efficiency in naturally ventilated buildings, and which are energy efficient as well. So this project is funded by the SEAI, and I'm working with James O'Donnell in this project as in UCD. So today I will be talk about what exactly the project is and what are the learnings which we got from this project, and how this project will help policy making and the decision making, and what are our vision for 2050. So basically this project is about collecting as much as data possible in naturally ventilated and energy efficient dwellings in terms of indoor environmental quality and energy consumption. So the idea behind this project is, when we talk about the residential dwellings, we individually focus on IEQ and energy consumptions. But we know that energy consumption and IEQ are highly correlated and they impact each other. So in order to have the comprehensive assessment of the residential dwelling, they should be considered together so that we have a comprehensive performance of the building. So our aim is to collect the data by deploying the sensors in the residential dwellings and gain the insights from how the indoor environmental quality is linked with the energy consumption, and model these in using the and model these using residential building archetypes, so that we can estimate the energy consumption and indoor environmental quality at the same time, so that we can pinpoint, okay, what are the time there is a overheating in the dwelling, or when the people are not thermally comfortable. So the methodology used for this study is we deploy low-grade sensors in 16 residential houses across Ireland, which are energy efficient, which means they are aerated homes and they are naturally ventilated. So for a period of 1 year, we collected the indoor environmental quality and energy consumption data using the low-grade sensors. And to validate the low-grade sensors, we also deployed high grade sensors for a 1 week, so that we can compare the low grade sensor readings and the high grade sensor reading for the validation and the calibration purpose. Once we have the data, we analyzed the data and used that data to develop residential building archetypes, so that we can develop machine learning models to predict energy consumption and IEQ at the same time. And this data, which we collected using the sensors, was used to validate our estimation results. And this is the setup which we use. So on the first image on the figure 4 is for the low grade sensors which we installed in the houses for a period of 1 year. The figure in the middle is used are the high grade sensors which are used to validate the low grade sensors, and the figure C is the energy sensor which we installed on the meter that is capturing the energy consumption data at 10 minutes interval. So the learnings from this analysis. So first is the indoor environmental quality analysis based on the sensors. So approximately for a year, from 16 houses across Ireland, we collected approximately 40 million data points, which is quite a big data set for our analysis. We found out that the IQ levels are governed by the occupant behavior. So it's not always if we have the proper ventilation or not. It is also the activities which humans do in residential buildings that impact the indoor environmental quality and the energy consumption. The CO2 data collected from the sensors can be a good proxy for the occupancy presence in the dwellings. And the natural ventilation provides very inconsistent air change rates. So it again, it depends on how occupants utilize the natural ventilation by opening or closing the windows, so that they have a thermally comfortable in indoor environments. And there is a large variations in IEQ between the summer period and the winter periods. And cooking is the largest source of indoor PM 2.5, and this is basically due to the insufficient ventilation during those times. Now, when we have all this IQ data and the sensor data, we use the residential building archetypes to model these, so that we can estimate them, so that we can predict the results using the models, because we cannot have these sensors all the time in the buildings. So for that, we use the residential building archetypes, but to accurately measure the results, first we developed the occupancy models it has a highest uncertainty when it comes to energy consumption and IEQ. So two types of models are developed: deterministic model and the probabilistic model. And then these are used for the multi-scale energy analysis. Then we also developed the meta model based optimization to predict and optimize at the same time, and it reduces the optimization time by approximately 80% with an accuracy of 98%. So now, how does this help in the policy making? So this study focuses on occupancy behavior and combined energy and IEQ analysis. So this will help in updating the standards so they match the real world values. And the meta model based analysis helps in identifying the various retrofit performance of various retrofit scenarios, very quickly. And these will support the development of robust energy policies which consider both energy consumption and the thermal comfort of the occupants at the same time. and what is our vision for 2050. So these models can be extended to integrate more renewables into the study, and with this we can develop more scalable and interoperable technologies like integrating cloud-based BIM and using the data-driven support tools to develop the policies so that they are data-driven, and then using the community-focused energy solutions. Thank you.
Presentation, I'd like to introduce Chitaranjan Sharma. So if you would like to show us your presentation, Chitaranjan. Great. Good to see you.
Right.
If you'd like to show us your presentation, and then you will have 7 minutes as well.
I'm not sure if I'm supposed to share.
Yeah. Okay. Great.
Yeah, good morning, everyone. Today I'll be talking about the operational stability and network-related strategies for large-scale deployment of solar PV generation on the Irish power system. So we're looking at Ireland-specific challenges, problems, and solutions according to that. Yeah. So to start off, the solar PV targets, looking at the targets for 2030 and beyond, we can see that for 2025, we have the new climate action plan target of 5 gigawatt and going up to 8 gigawatt by 2030. And if we compare the figures on compare the figures with the previous targets, that is around 1.5 gigawatt for the 2030. In the figure also, we can see that the amount of solar PV generation that is shown here in the red dots over here, the difference in the amount, and also the location is also quite a bit important here, because most of these solar generations are kind of coming in on the east coast and the southern part of Ireland, whereby previously we or currently we have a lot of wind generations on the west coast, and that is going to create a lot of new challenges for integrating or a rapid integration of such large-scale integration of PV systems. And one important thing to consider is the differences in the overall profile of PV, the generation profile, and the technology involved itself involved in this type of generation. So coming to the challenges specifically for Irish power system, if we look at the first graph, we can see that the dispatch down of wind energy wind energy in the overall last 10 years or so, we can see that with the increase of the capacity of wind, then we can see that the dispatch down generally has an increasing trend. So eventually with the increase of PV in the Irish system, definitely this trend in increase is going to be more becoming more worse. So if you look at the figure on the right side, we can see that the net demand with PV in the Irish system for a summer day representative day on the 2030 compared to a winter representative day. For the summer day, we can see that the net demand has kind of dipped. We can dip quite a bit in the middle, kind of bringing a lot of challenges in terms of for example, the ramping down and ramping up of other generations that are going to pick up this slack. And also, for example, this also creates another opportunity, for example, for EV to be charged in terms of the filling in the gaps in between the middle of the day. So here, in terms of challenges, we are classifying the challenges in terms of system level challenges, and for example, in terms of regional challenges. So if you look at the system level challenges, we are looking at multiple things here. For example, balancing frequency control, stability, dispatch down of renewable energy sources that is to be maintained, for example, at around 7%. Anyways, these sources like PV or wind, for example, that is more or less the same, does not provide any system service provision. For example, for specific to PV, we have the problem of spatial and temporal variation of PV output, the ramping effects that I just talked about just now, and also possibility of having low wind and low PV at the same time. So those are some of the system level challenges. And if we look at the regional network level challenges, we are looking at local overvoltage, local overloading, possibility of regional hotspots and power quality issues that eventually reduces regional RES or renewable energy sources hosting capability. So if you look into these various challenges that are, kind of segregated into system level and regional level challenges, the overall project methodology that we have is adopted something like this. So if you look at the first top half, we can see that the impact of high shares of PV on the iris grid is studied first, with spatial and temporal distribution of PV being analyzed as the first instance, and developments of network models are carried out to identify regional and system-wide issues in the whole system. With this work being done, we now come into the system services that can be actually provided by PV services, PV systems for the iris grid, that can include grid forming capability, fast frequency response, voltage support, system strength, inertia support, black start, fault current, and all these studies are going to be carried out with EMT simulations for the performance analysis of this system. So now that we have looked into the challenges and we have looked into services that can be provided by PV systems, we come into the challenges and solutions for regional level and the system level. So at the regional and system level, we are also grading this type of challenges based on the increasing share of PV. So those challenges that we have discussed earlier are graded over here based on the share of increasing share of PV. And then we are going to be looking at various studies for regional level. We are looking at RMS and average simulations for selected regional networks. And we are also looking at EMT time domain simulations using OpenLRT hardware in the loop. And also at the system level, we are looking at optimization study at the various iris grid scenarios for multiple weather years to maintain dispatch down levels, coordination with various renewable energy sources, and looking into transient stability analysis of various case studies. And the outcome of the study that we are looking for over here is solutions for regional and transmission system operators that can be in the form of grid code modification, policy changes, and the end user will be ESB networks and air grid. So coming to the current work of optimization and simulation, we have just started off this project very recently. So currently we are still starting off with a few of the optimization work and some simulation that are being currently planned. So if you look at the optimization model, first of all, we are looking at developing or getting regional time series data that will go into the optimization model that has a unit commitment with operational constraint and contingency screening that can give a representative result that is shown over here for the winter and summer months, showing you the curtailments at various regions of the iris network. For the simulation model, we are looking at starting off with something like the dynamic system model that is shown over here. That is the single frequency model, where we get the input from the optimization model in terms of dispatch and in terms of commitment to be fed into the EMT models of the thermal generations or different renewable energy sources. They are used to create this simulation model for various analysis.
Yeah, if you can, come to your conclusions, that would be great, Challenging. Thank you.
So the overall objective is a comprehensive approach to identify Ireland-specific problems and solutions for 2030 and beyond. And at the system level, we're looking at stability, maintaining dispatch down, optimize economic solutions. At a regional level, we are looking at maintaining headroom for rapid and continuous uptake of PV, looking into 2025, 2030 and beyond. The solutions looking ahead to 2050, we have advanced solutions such as grid forming capability, providing system strength, like start capability, fault current injection, and we are looking at a little bit more detailed EMT simulations of networks and components with various softwares, etc. So that's all. Thank you.
Thank you very much, Jonathan.
Thank you.
And now I'd like to welcome SEAI, and Emer's going to talk to us about testing marine renewable energies at scale. Hi, Emer.
About the offshore renewable energy infrastructure that we have in Ireland and its importance to the industry. So to achieve scale up and commercialization, testing is required and provides a significant benefit to the industry to test at various different scales. And this is to keep costs manageable for prototypes while simultaneously both validating designs and models and learning by doing. So facilities which enable the testing of offshore renewable energy technologies are at a range of different scales, but each scale would play an important role. And I think if you can just move, thank you, yeah, sorry. These are the different test site infrastructures in Ireland. There are 3 different sites being developed or either in operation. And the technology readiness scale is from 0, which would be concept design, right up to 10, which is your full-scale technology ready to be deployed commercially. And in UCC, so in Ringaskiddy, actually, County Cork, so you'll see on the bottom of the slide here, there is the Lear National Ocean Test Facility, and that is a small-scale site that includes deep water basin and test tanks, and that's for testing technologies from TRL levels 1 to 3. For mid-TRL level technologies, there is the Smart Bay test site in Galway Bay, and that is run by the Marine Institute, and that is for testing a mid-scale, so for TRL level 4 to 6, and it is a sheltered site there, even though it is a saltwater environment. And then off the coast of Mayo, SEAI are developing the Atlantic Marine Energy Test Site, or AMITS, and that is for full-scale grid-connected ocean test facility. So we are talking technology readiness levels of 7 or above there. And this is, it's a harsh marine environment, but it has really good energy resource, both wind and wave. So it's valuable for testing multiple different technologies and while simultaneously connecting to the grid there. So that is in development. So the test facilities allow for validation and refinement in design, but also data. They provide data for certification of a particular technology and performance data, which would help with, I suppose, bringing your technology towards commercialization. The real-world experience of installation, operation and maintenance also help to advance towards commercialization. And we don't only test generating technologies or devices. What we test, there's also components, subsystems and moorings, and also regulatory regimes, which would be the opportunity to have what's called regulatory sandboxes, which are controlled real-world environments which provide structure and context for direct testing of innovative technologies, but also products or services or approaches under regulatory supervision. And there is lots more information on the test or on the website here, so Ocean Energy Ireland. And also I just wanted to briefly mention the recently published Offshore Renewable Energy Technology Roadmap that is available on the SEAI website, that goes into more details both on the regulatory sandbox and also on the test sites, as well as the sector more broadly in Ireland. So that's an interesting read. And I'll hand you back to Emery now. Thank you.
That's great, Emer. Thanks very much. So that was really interesting. Just want to remind people about, just if you have any questions, we're going to go to Jimmy Murphy next for his presentation, and then we'll have a question and answer session. But if anybody does have any questions they'd like to ask, please let us know and send them through. Thanks very much. Over to you, Jimmy.
Sorry. Okay, I thought everything was done automatically. So yeah, I'm going to talk today about an SEAI funded project called Atlantic Float, and it's floating offshore wind technologies for the Atlantic environment. So this is an industry university joint project, you know, so it has University College Cork and the Murray Centre plus MTU and the Halpin Centre, you know, as universities, and then it has 3 industry partners, which is Rockall Research, Wind Energy Ireland, and Dublin Offshore Consultants. So I suppose to give context to this project is that, you know, so we're on the cusp of fixed offshore wind development, primarily along the East Coast, but our real potential for wind energy offshore is in floating wind. You know, sort of the OREDP2 identified maybe 10 times the resource in floating wind than in fixed wind. So, you know, sort of we must prepare and be ready to develop floating wind, and this is what this project, which is funded by SEAI, intends to do. We're looking at, you know, technologies that can survive, operate, and be maintained in Atlantic and Celtic Sea environments. You know, so just identifying or just showing you what the challenge is, you know, sort of in terms of working off the south and the west coast of Ireland. You know, sort of we've done this analysis here on, first, if you look at the picture on the left hand side, you know, so you'll see extreme wave heights, you know. So when you go off the southwest and west coast of Ireland, you are seeing 50-year significant wave heights of 14 meters plus, you know. So when you need to put technologies that will survive and operate in those sort of conditions. So they're environments that are way more extreme than anything that has been done before, and where platforms have been placed before. So obviously, you know, there are challenges in getting the platform out there, even getting the turbine manufacturer to supply a turbine to go out there, and then if it's out there and it breaks down, how do you maintain it? And that's kind of highlighted by the other picture there, which shows the weather windows, you know. So you know, if you want to get out to an offshore platform in the winter time, this shows that, you know, you'll get a 6-hour weather window with a wave height less than 2.5 meters about 10% of the time. You know, so you have very little opportunity to do things offshore in the winter. So you must design your technology and your logistics and your methodologies to be able to work in this environment. And that's the challenge we have, and that's what the project is addressing. So just to say what we're doing in the project, we're looking at different floating technologies, you know, sort of, and we're modeling them in a laboratory environment at the Lear National Ocean Test Facility, and doing it numerically as well. So the main platform that's being used at the moment is called a semi-submersible. So we're taking generic designs for a semi-submersible and a TLP, which is a tension leg platform, and then we're identifying and measuring how they behave in Atlantic environments, and then, you know, sort of, you know, based on what we get, we'll design a new platform. So, you know, part of the project is to design new technologies that will be able to survive and operate in Atlantic environments. And that's what our 2 of our industry partners are doing. You know, Rockall Research are designing a stable offshore floating wind platform called SoftWind, you know, sort of particularly for Atlantic environments. And that's a picture of it, you know, and if you look at the picture there on the right, that's it being tested already in the Lear National Ocean Test Facility. And then Dublin Offshore are developing this mooring system, or component of the mooring system, called the LRD, and we're incorporating that into it as well. So they're the main things coming out of the project. You know, we're identifying behavior of technologies in ocean environments, and then identifying you know, sort of developing solutions for it. You know, so just how we'll sort of inform policy, you know, and the benefits of the project is, you know, sort of we'll identify the readiness and challenges related to development of floating wind farms in Atlantic sites. This may influence the timeline and site locations for the first floating wind farms in Ireland. I know there's a push for wind farms, particularly along the west coast, you know, floating wind, but my view at the moment is that we're not ready for it yet, you know, sort of, and the project as well, if you look at the second bullet point, is that, you know, we'll have more information on the behavior of technology offshore in terms of failure rates and loadings and things. So we'll be able to give more reliable estimates of the levelized cost of energy, you know, sort of for floating wind in, you know, sort of extreme environments. And also, you know, because we're developing new technologies, we're contributing to development of the Irish supply chain, and also providing data knowledge, you know, sort of to the sector in general. So my last slide here is just sort of identify, you know, sort of if we're looking at rolling out floating wind on a large scale basis by 2050, you know, what do we need to do between now and then to make it happen? And I've just shown a picture there on the right hand side, you know, sort of a, you know, sort of what is now the largest floating wind platform in the world. You know, sort of it's a twin turbine platform, and there are two 8.3 megawatt turbines in it. And we tested that at the Lair National Ocean Test Facility in 2019, and now it's a full-scale version of it has been deployed offshore in China. You know, so I can show you know, sort of we can move fast. You know, or that the industry can move fast if there's, you know, sufficient will and resources available to do so. And I suppose a bit of my point is that you know, sort of Ireland, we want to be a world leader in doing things and developing technologies and moving forward in floating wind. But you know, so we won't be unless we start moving now. You know, so my main message is that we can't delay and put things off and take a long time. We're not very good at putting things into the water. You know, sort of. So we need to move faster than what we are. So to be able to do that, you know, in terms of research, we need to understand technology performance and operational limits. And then based on knowing that, we can design innovative solutions, you know, to cope with the environments that they're going out to, particularly Atlantic environments. You know, floating wind still doesn't know the best way to install and operate, you know, wind farms. So we need a lot of work in doing that. And then as well, you know, sort of, I know that Emer was talking about the test sites, you know, that there's various things happening, you know, sort of, Emer mightn't have talked about what this float-out project, which is an infrastructure that's been funded by SFI and SEAI, is to put a floating 200 kilowatt platform in Cork Harbour, and that's being managed by the Marai Centre in UCC, you know, so that'll be an infrastructure along with, you know, sort of, I hope Smart Bay and Amets, you know, overcome any challenges and get operating again. So we need to test technologies in real environments to develop them further. And also, you know, the last two things is obviously to improve collaboration, you know, sort of between industry and research and government. You know, the sharing of information is critical in order to move forward. And the last thing then is, you know, sort of there's plans there for a floating demonstrator, maybe a 200 megawatt plus wind farm, you know, sort of, to be good if that was fast tracked and moved forward, you know, sort of, and then with its development, you could link research and innovation and data sharing with it, you know, so and based on the learnings, then you can, you know, advance the sector and have Ireland, you know, more at the lead of it than trailing behind the other countries. So I suppose that's my presentation and my message from this. So thank you very much.
Great, Jimmy, thanks very much. We now have a bit of time, so we're going to take a few questions. So the first question that I've received is for Virkam. So Virkam, how are wind farms performing compared to their expected lifespan? And then also, are turbines degrading sooner than expected?
No, the turbines are not degrading sooner than they're expected. You have to understand the lifespan that we expect for wind turbines. It's quite conservative. So if not anything, I would say the question we might be asking is like, can we make them last a little longer? Can we squeeze the juice out a little bit longer? What's interesting is that sometimes we don't know within a cohort of wind turbines, are they degrading at a similar rate? Are they degrading at a different rate? And if some rapid assessment, like the way we are doing, shows that actually they're not too bad, they're kind of degrading at the same level, one great thing could be that you could take a representative turbine, you could instrument the whole thing up in detail, and that would represent things at a farm level. So I would say remaining service life is the question that we should be asking. And in fact, it is the question lots of other farms are also asking, and they're carrying out at a regular level. But it must come with sensors, must come with testing.
Great, very good, Vikram. Thanks very much. The next question then is for Divyanshu. So when measuring air quality, how did bedrooms, as in those breathing during sleep in one room, creating lots of moisture, compare with the rest of the house and say the kitchen? So that's quite an interesting question.
Yeah. So what we actually measure was like the indoor, like the temperature, humidity, CO2 concentration, and PM 2.5. And in bedrooms at night time, when there is when there is no ventilation, they become quite worse in terms of higher CO2 concentration as the occupants are in the bedroom they are sleeping. So in some cases we observe that people woke up at night and they open the windows to read. So we observed in in the sensor reading that CO2 drops. So there we talked to them and we saw like, okay, when we observed that okay, they woke up and they opened the window and then they feel much better. And in terms of, if you talk about the kitchens, that in during the daytime it remains quite okay, but whenever they are cooking or they are using the stoves and their windows are closed, then that time the PM 2.5 and CO2 basically the PM 2.5 it increased drastically.
Okay, very good. Thanks very much for that, Divyanshu. And the next question then we have is for Chitaranjan. What parts of Ireland are approaching grid limits in terms of solar PV development? I don't know whether that's...
Yeah, currently we are still not hitting, with my knowledge, I don't think we are hitting any limits for now, but I think we are starting to see some problems. Like I talked to some of our project partners, for example, in ESB networks. And one of the things that they are facing right now is something that we thought that we will face at the end, like almost at the end of the 2030 targets, that is power quality issues, that things like power quality issues are creeping up right now, that they are kind of looking to multiple ways of solving, installing power quality measurement devices. So at the moment, it's just starting off the ramping of PV to reach the 2025 and 2030 targets. But as of now, I have not much, I don't know much of if there's any much issue at the moment yet.
Great, that's really good. Thanks very much. And we have a question. This is for Emer. And the question is, can floating offshore wind be tested at Smart Bay?
Yes, it can be tested at Smart Bay, and I think they had looked at that in the past, and I'm not sure if there are plans there at the moment, but floating offshore wind could be tested in any of the test site infrastructure.
Yeah. Great, that's great. Thanks very much. And one more question. This one is going back to Virkam again. And the question is, apart from monitoring degradation and behavior of wind blades, are you considering to use various plastic-based composites to manufacture blades? For example, the ilium resin as the matrix of composites.
So in this project, we are not manufacturing anything. We're looking at already manufactured blades and their assessments. So we're looking at it in three ways. One is the drone assessment, as you've seen. The second one is there are lab-based testing to visualize how these things happen within scale tests using particle image velocimetry, where Professor Kevin Nolan in UCD works with us a lot. And then there's a third very interesting thing led really by Munster Technological University professors Vesna Yaksic and then Kieran Ruan, who's also doing a PhD in UCD. They use and there's also a company now called they use wind turbine blades repurposed as bridges and other second life for structures. And that's something we are also assessing, which is really important in terms of materials, because its life as a wind turbine, that's gone. But in the second life, we need to know what capacity does it have, what consistency does it have in terms of as a material, as a structure. And that's a project that I really enjoy working with. So these are the three ways that we're looking into it, but we don't manufacture the blades. It's a very important note here. But there are lots of uncertainties around the materials that are being used. Everything that was asked in the question, I mean, they all come with their fundamental uncertainties. And unless we have enough data and we characterize them, our conclusions on the blades will have that uncertainty inbuilt into them. So that's important to note.
Great, that's really good. I have one more question. I think we have time, and that's for Jimmy. The question is, many of the challenges for offshore TLP and SSP have been addressed in oil and gas industry. Are there learnings we can adapt or adopt from those industries?
Well, I suppose the oil and gas industry, for one, sort of that it's a different type of industry, and it's been characterized by the abundance of money. So, sort of when you're looking at a wind farm, you're looking at, sort of maybe 50 plus units that you must install, whereas oil and gas, sort of is single units, that are deployed, or even a low number. So there are different challenges when you want to put a large number of sort of floating platforms in place, so indeed there are learnings from, sort of existing TLPs, existing semi-sub platforms from the oil and gas sector, but the designs that we have for floating wind are different in terms of the size and the scale and their characteristics as well, sort of, so, and the installation and the O&M, all these are different, sort of, and as I said in my presentation, sort of, we do not know yet the best way to install a large wind farm, sort of, say off the coast of Ireland, or, sort of south or west coast out, and using the harbours as well and the ports, and how they'll be fitted out to be able to cater for the floating wind installation and O&M, sort of, and also there's a situation where you need sort of wet storage as well to store platforms prior to they being towed out offshore. So there's a large number of challenges that exist for floating wind, logistically and operationally, that need to be solved, sort of that didn't exist, say, for the oil and gas sector, even though the fundamentals of the platform itself in terms of their behavior are the same.
Okay, very good, Jimmy. And actually somebody snuck in one last question for Jimmy, sorry about this. But the question is, how is energy from the floating devices brought to shore?
Okay, so it's the same as for any wind farm. There'll be cables and substations offshore, sort of that'll run to the shore, so that's the standard way. It's a bit more complicated with floating wind because you have to have a flexible umbilical, sort of going from the platform to the seabed, sort of, and you have to design that as well, but those cables from the platforms run to a substation, which then runs a bigger cable then to a shoreline substation. There's talks about having platforms that will just produce hydrogen as well, so that may be a different vector down the line, sort of, but at the moment it'll be all transmitted through power cables.
Very good. That's great, Jimmy.
Could I chip in for 1 second on that one? So SEAI has very timely actually funded a project on offshore dynamic cables, where both Jimmy and I participate. It's just started about a couple of months back. So it's a very timely question and a very timely response by the SEAI in terms of its funding for the project.
That's great, very good. And thanks very much to all of you, Virkam, Divyanshu, Chitaranjan, Emer, and Jimmy, for great presentations and for answering all the questions. Really appreciate your time and your inputs. Thank you.
Thank you.
Thank you.
And now I'd like to welcome our next speaker. So we're going to have another 5 speakers, and then we'll go into Q&A session as we've just done. So the next speaker is Niamh O'Sullivan from SEAI, and Niamh is going to be talking to us briefly about district heating. Thanks, Niamh, and welcome.
Hi, I'm Marie, and thank you very much for having me. It's great to hear all those talks about the scale of the offshore challenge, and I suppose I'm going to talk about the challenge in decarbonising our heat sector, particularly. So I'll just jump on here to the main, I suppose, starting point, and here I'll start with the numbers, and I guess this is an important place to start in terms of why we need research in terms of decarbonising heat. So the numbers are quite stark. Currently, 90% of our heat comes from fossil fuels, and that contributes to approximately 21% of our greenhouse gas emissions. And we're currently in last place in Europe in terms of renewable heat. So these are our numbers, and they're really, really stark, and they're not consistent with our goals. We're behind the curve, and we need to do better. And the simple fact is, you can do better. Today, I suppose, just to focus on this slide, just the very center of that bar chart shows, I suppose, that today that's the component of our heat that comes from renewable energy. And as you look out towards 2050 on the right-hand side of the graph, we're going to need that component to increase by a factor of about 4 to get to 2030 and significantly beyond that into 2050. But the good news is that we do have the technologies and the know-how and how we get there. And I suppose, like Jimmy said, sometimes it's difficult when we have to do big things in this country. And the 2 levers that were identified successfully from the SEAI National Heat Study, the first comprehensive framework of how we should decarbonise heat, identified heat pumps and district heating as the main levers. So you might be more familiar with heat pumps, but district heating is not a new or novel technology. It's very, very, very popular in the continent, and particularly with countries that have a high renewable energy share in their heat. It simply involves heating hot water at a central location and distributing that by insulated pipes to homes and buildings, and where it interfaces with your heating system. So instead of burning gas or oil in your home, you would instead receive this hot water and then draw down that heat. So I suppose then we know that district heating, say, is one key area, and this is where SEAI has decided to focus some of our research in recent times. And we've done two significant projects, I suppose, that I'll just touch on today. And it really involves, if you consider the funnel, I suppose, of projects that we need to deploy. So our targets are around, the target that's set for 2030 is 2.7 terawatt hours. And that equates to around 100,000 buildings being connected by 2030, which is a big number. It's about 90,000 residential, for example, and 10,000 kind of public sector and commercial. So the first thing we undertook was a sort of big energy master planning exercise, I suppose, and we did a nationwide data crunch on the heat demand across Ireland. And this identifies, on the right-hand side, you'll see the map of Ireland, identifies the areas where it looks like it could be viable to do district heating. And all of these would coming together would give us our target of 2030. The second thing then, I suppose, if you want to narrow that funnel even further, you've identified an area that might be viable, you've got an idea. How do you then test if it's viable and has merit and should be worthy of further investigation? And this is where you'd undertake a feasibility study. And SEAI has undertaken research with CODIMA in terms of looking at international best practice and developing a standardised assessment and approach and methodology. And I suppose the idea being that you could rapidly screen potential projects to see whether or not they will be worthy of further investigation and further work. So if you could imagine, if you just take a big step back, we might need 100 projects across the country. That might mean you might need 300 feasibility studies, and you need them to be done rapidly and at scale and to a similar standard. So shortly we'll be publishing via our new Centre of Excellence for District Heating. They'll be able to share this standardised template and also a very detailed and comprehensive how-to guide, recognising that it's a fairly novel technology in Ireland and that we need to offer guidance and assistance. And this is where this research, I suppose, will be key to accelerating the deployment of this key infrastructure out to 2050. So district heating is key, and SEAI is going to continue researching in this area and trying to identify those gaps and to close them. Thank you.
That's great, Niamh. Thanks very much. Thanks for that. Next, I'd like to welcome Sophia Tosoko to the research sprint. And Sophia is going to be talking to us about future integration of anaerobic co-digestion of grass silage and cattle slurry within a livestock farming system in Ireland, which will be very interesting. And Sophia comes from the University of Galway, so we're very much looking forward to hearing from Sophia. Welcome, Sophia.
Hi, thank you very much. So I'll be seeing, yeah. So yeah, as Anne-Marie mentioned, my name is Sophia, and today I'll be talking about my research, which is the integration of anaerobic co-digestion of cattle slurry and grass silage within a livestock farm system in Ireland. So there's an opportunity in Ireland as pasture-based beef farms can produce cattle slurry and grass silage for anaerobic digestion, but there are some challenges that come along. For instance, the sustainable production of grass silage, the feedstock provision into a full-scale plant, considering that Ireland has relatively small plants, the financial viability and support at a farm and supply chain scale. So the research objectives of this study were to assess the farmland area required to provide slurry and grass silage into a 40 gigawatt-hour biomethane plant, quantify greenhouse gas emissions, analyze digestate management and assess the economic analysis of biomethane production at a farm and supply chain scale. So a bit of study framing. So the model used in this study is the Grange Dairy Beef System model with incorporation of an AD submodel, and this was used to calculate the feedstock production per hectare, so the slurry and grass silage production per hectare, and each farm assumed to have 50 hectares available to farm. So this information was used to calculate the total amount of feedstock required by a 40 gigawatt-hour plant co-digesting slurry and silage at a volatile solids ratio of 20% and 80% respectively. And then digestate was assumed to be returned into the farms, providing the feedstock, and a soil index of 3, which is considered an soil index which has medium to optimate concentration of phosphorus and potassium in the soil was considered. So in terms of the financial analysis, so 2 scenarios were considered: a baseline scenario, in which only the plant only had biomethane certificate as a potential support, and a grant scenario in which the plant contained the biomethane certificate as well as capital cost grants, grass grid connection grants, and a silage subsidy to establish the grass silage crop. And then capital and operational expenditures were calculated for the AD plant, as well as the net present value over a 20 years project lifespan. So as a bit of the results, the AD farm configurations, so it was found that 85% of each farm would have to be dedicated to have livestock to produce the slurry for the AD plant, whereas the remaining 15% would be dedicated to grow grass silage for the AD. And if we have 130 farms with this same configuration, we will reach the annual feedstock demand by the AD plant. And as greenhouse gas emissions, so at a farm level, it was found that greenhouse gas emissions could be reduced by up to 24% if 15% of the land is dedicated to grow grass silage for AD. And in terms of the digestate, we found that returning back digestate to the farms reduced the chemical nitrogen, phosphorus, and potassium application by up to 65, 33, and 56% respectively. So as for the financial analysis, so looking at the net present value over 20 years, it was found that neither of the scenarios investigated led to an attractive financial situation. So a further scenario was analyzed. So a further analysis was carried out, and this included, so what is the maximum price that the AD plant can pay in order for grass silage in order to achieve an attractive financial situation. And here is the black bar, so the maximum price that the plant can afford, and the price gap between the maximum price that the AD plant can afford and the grass silage price needed would have to be compensated through farm subsidies. So the price in this study, the price that the farm would need to make this a business, also attractive business for the farm, was €245 per ton of dry matter in terms of the grass silage. So a bit of outcomes of this research. So we looked into the farmland area required to produce feedstock into a full-scale plant. So also the greenhouse gas emissions at farm and supply chain scale level, and also in the economic part, so what are the grass silage price needed, and what is the biomethane certificate price needed to make all this financially viable. So the impact of this research on policy making and energy future. So this research impacts on different sectors, starting from the farms. It provides information about how farms can diversify by producing grass silage, but what are the economic numbers that would make this feasible. The industry, it provides information for the industry by looking at the biomethane certificate prices that the industry would regard to also make this financially viable. And of course, the most important, the policy, it provides information for policymakers so they can provide adequate incentive and support mechanisms for the sectors involved. And of course, the bigger picture is Ireland, and it is working towards a sustainable and low carbon agricultural sector and energy future. So last, my vision of the research. So I see all these as a mix of combination of different gears that are moving together and they need each other to move. So the research outputs is the one that I'm part of. I'm as a PhD researcher generating information, but of course that to do research, I also need from other previous data results for previous colleagues that have been working on the area. So in this, I highlight the importance of collaboration, of engagement, of knowing what other groups, research groups are doing to see if they can complement your research. And of course, the knowledge transfer is a middle gear, which is gaining visibility of our research, and platforms like today are very important to achieve this. And well, the biggest gear of all is securing our energy future and our environmental future for 2050. And for this, we all need, as I mentioned, cooperation, engagement, collaboration, and make this work together. So this was all that I wanted to share. Thank you very much.
Thanks very much, Sophia. That's great. Very interesting presentation. I'd like to go next to James Clark. So James Clark has got another very interesting presentation. This one is tackling energy poverty through retrofit analysis. So welcome, James. Great to see you, and looking forward to hearing about all of your work and how that kind of links in or lines up with our 2050 ambitions. So thanks very much.
Thanks for having me. So as mentioned there, my name is James Clark. I'm working with Prime 19. It's an Irish startup in the analytics space. So what we've done as a trusted partner of the SEAI is develop a tool set that allows homeowners to understand their building energy rating or their BER rating better, so they can understand where their home is falling down in terms of its energy efficiency and understand the steps that they can take to improve it. So we've been developing this tool over a number of years, and it's quite a good tool that households can use in order to improve their energy rating. And so that ties in naturally kind of to the project, which is tackling energy poverty through retrofit analytics. So kind of using this tool set in order to kind of tackle energy poverty in the country. So just as a project overview, so the aim of this project ultimately is to reduce energy poverty. And I suppose this will be done through kind of identifying and characterizing energy poverty. So through using BER data, we're able to estimate people's monthly energy bills. We can also use other censusing data to identify what the household income is likely. So we can identify where areas of energy poverty are. And the project structure is laid out there below. I suppose the first step here is developing this data set to identify ongoing analysis of energy poverty. The benefit of that is that we can have an up-to-date view of what energy poverty looks like in the country. So we can update, the fuel price changes as they happen, and we can update the BER information as it comes in to understand, how the residential portfolio, household portfolio is changing and how the fuel prices are changing to understand how that's impacting energy poverty. So we've looked at that, developed that tool. We've gone through, identifying what are the characteristics of the risk drivers of energy poverty. The next step for us now is to understand what the most effective method of reducing energy poverty is. So this will be using the software that we've developed, where we can put in a home and understand, what steps that homeowner needs to take to move from a BER of, C2 up to B2 to get it up to the improved standards. If a house doesn't have a BER, we can still deal with that, where we ask some basic questions to the homeowner. Things like, when was the house built? What's the main heating system? Things like that, very basic questions that the homeowner would likely know about their own house. And we can model a BER data set for that home. And we can use that to then make likely recommendations. The big aspect of this project, I suppose, is communicating, particularly to local authorities and approved housing bodies. So one of the issues they may face when dealing with retrofitting homes that are under their care or dealing with energy poverty is that they might be dealing with a huge amount of houses. And in order to provide, solutions, it's quite a manual process going into the homes. doing the review, coming up with the plan, going back to the home to make sure it works. This software allows that process to be streamlined and to be done kind of en masse with the tool. The final step then is just to implement the changes and assess the impacts and to see what can be improved, what can't be improved. So it will be an ongoing process. The motivations for this research, the first thing is obviously to help to reduce energy poverty. Obviously in recent years, there's been massive fluctuations in prices of fuel, and we're kind of explaining what that looks like, how that impacts people that are at risk of energy poverty. And the second thing is supporting Ireland in achieving its sustainability targets. So, the goals for 2030 is that 500,000 homes need to be retrofit to B2R and 600,000 heat pumps need to be installed. Obviously, that's very kind of big targets, and it doesn't put any kind of specificity on where they should be happening. So our tool kind of allows specific areas that will get the most benefit from retrofitting or the most benefit from the heat pump, allows us to identify those areas. This is just a quick analysis on a particular small area. So this is Naas, and we've just pulled out here. So you can see the map here across the country showing, the areas of high energy poverty and low energy poverty. In particular, we're looking at Naas here, and we can see, what the number of homes are in Naas, the number of households that are there, the number of households with B, or we can get things like, the number of houses that are heat pump ready, and the average boiler efficiency in this area, the average income in the area as well. So this is kind of quite a powerful tool that we can use to deep dive into very localized areas to see, what measures need to be taken in order to improve the energy poverty profile there. So the next step is just an impact on policy making. So these are just, the people that we'll be engaging with for the project. So as I mentioned before, a lot of the benefit of this is that things can be done en masse. So, we'll likely be communicating to residential households in order to inform them of what strategies they could take to maximize benefit for themselves. So a very kind of bespoke strategy for households. We'll be engaging that with the local authorities and approved housing bodies, because this will be a huge benefit to them. We can streamline a lot of the work that they will be doing in order reviewing their household portfolio. And then we'll be engaging with the SEAI. So there's kind of ongoing engagement with the SEAI in relation to things like their energy master plans, as well as the national retrofit plan. So this kind of centralizes a lot of that work. Sorry. Jeez. So the current position is that, we have approximately 2.1 million homes in the country. Of them, apparently approximately 1.1 million have BER certificates with an average BER of C2 to C3. As we move to the 2030 action plan, a lot of houses will be retrofitted, the BER profile will increase and more houses will get BER. I suppose where this could go in the future is that we can actively monitor the housing portfolio to identify kind of houses that are likely to fall into energy poverty before it actually happens, to kind of, be very proactive and ultimately eradicate energy poverty in the future. Thank you very much.
That's great. It sounds like an early warning system, which is good. Thanks very much for your presentation, James. That was really excellent. Us about smart LEM supporting Ireland's energy transition. So welcome Tudor, and Tudor is coming to us from Open Sky Data Systems. So we're really interested to hear your presentation and looking forward to learning what you have to say. So thanks very much for joining us.
Good morning, everyone. I will present you today a European funded project, Smart Local Energy Market. It's a clean energy transition partnership project. And as any European project, it's an international collaborative effort, and our goal is to contribute to the accelerating the energy transition. The project has started, actually has the kickoff meeting in Bucharest in May 2024, and It will be a 3 years project. We are 10 partners, 4 universities. One is in Bucharest, the University of Economy in Bucharest, which is the leading partner. Technical University in Vienna, Technical University in Barcelona, 2 important grid operators, 2 SMEs, one being Open Sky Data Systems for Ireland, and 2 city halls. You can see that we can try to cover as many important stakeholders as possible. I believe that you are familiar with the concept of local energy market. There are other similar, not identical, but similar concepts like positive energy districts, or the one that attracted me in this area a few years ago, meaning the sustainable energy communities, to a meeting in Brussels discussing about the use of blockchain technology in the public sector. It was a very interesting presentation from the Netherlands of sustainable energy communities, you know, using blockchain. Blockchain enables smart meters for putting in contact all the prosumers in a beyond the grid community. We will develop a digital platform for local energy markets, and the main goal is to support the stakeholders, local stakeholders in energy trading, because you know, as a small prosumer, it's your life could be quite difficult with the giants around. And I will briefly give a Romanian example, but the lessons learned could be used anywhere else in the EU. If you look at the comparative charts in Europe regarding the generation of renewable energy, you can see that Romania stays quite well. But if you look closer, you can see that there are a lot of issues there. For instance, this summer, which was very sunny and hot, during the midday, the grid operators need to pay partners in the countries around to use the energy because the grid was overloaded. And of course, this was difficult for the prosumers. And after a few hours, the same grid operators need to pay a lot of money for energy. So the explanation is that in Romania, they have not paid attention for storage capacities. So this is the main issue, and we will try to support, as I said, local energy markets with this digital platform. Of course, one outcome is to enhance grid flexibility and resilience, and of course, we'll try to offer actionable insights for policymakers. We will provide, of course, data and insights for those who are preparing energy policies. We will create this innovative solution. And of course, the idea is to have a long-term impact by demonstrating the viability and benefits of the local energy markets. Regarding the future, definitely the technological innovation would have a very important impact, especially advanced artificial intelligence and machine learning technologies, because it will be very important to predict demand and to optimize real-time trading. Innovation in storage, in energy storage would be as well extremely important in order to ensure stability and reliability in a renewable dominated grid. And we consider that decentralization would be the norm, because energy systems will likely be highly decentralized, and local energy market would be extremely important for optimizing the generation, the storage, and the usage of energy. And this shift need to be supported by citizens, by small prosumers, and we need to offer them incentives for adoption of renewable energy sources. But we can use here a term in international relation like fragmentation. It's about fragmentation with local energy market, but we need to understand that we are in the same huge grid, if you want. So we need to pay attention in the future to this cross-border energy collaboration. Yes. And it is very important to have in mind that policy and regulation need to be to pay a lot of attention to the market in general, to the economy, because we all saw the recently released so-called Draghi report, highlighting the fact that it is not extremely wise to establish from an office in Brussels some targets and afterwards to believe that the economy would follow and will fit in the framework that you presented. So it is very important to pay attention to policy and regulation. And finally, because we are all living in the same on the same planet, we need to pay attention to the United Nations Sustainable Development Goals. Thank you very much.
Thanks very much, Gunnar. That was really great. And you kept to time perfectly, so well done. We'll go next to our next speaker. And this is Emer Dennehy. So if you would like to maybe tell us a little bit about your work. You're coming from Trinity College Dublin, and yeah, we're really excited to hear about, does tailored information on potential cost savings and emissions reductions impact likelihood of switching to an EV? So take it away, Emer.
Yeah, thank you so much for introducing me. My name is Ubad. So I'll be talking about does tailored information on potential cost savings and emissions reductions impact the likelihood of switching to an EV. This is basically a project called Tracked Transport Behavior Change Trials that is funded by SEAI, and it is a 3-year project that is led by Professor Brian Caulfield. So on behalf of the team, I'm here today. So let me just first go give you an overview of the project. This is an interdisciplinary project, and we have teams from civil engineering department, psychology department, computer science department, and industry partners as well. The overarching goal of this project is basically decarbonization in the transportation sector. And we are actually targeting the climate action plan. And this is one of the 2 themes that is electric mobility. We are focusing on electric mobility, how we can transit towards electric mobility and the targets that have been set. The other theme is related to shared mobility. So I will not be talking about that today. I'll be talking about the electric mobility. And the objective of this piece of work that I'm sharing today is that we have developed an app called Track EV. It's a smartphone application that is available on both Android as well as Apple Store. And the trial is going on right now. So the idea is to actually see whether personalized information can lead to behavioral changes towards EV, because we have seen a lot of miscommunication and misconceptions about the EVs in the market. So you all are aware about the avoid, shift, improve policies. So we are targeting the shift and improve aspects of it through trialing. So if I just go to the basic structure of the app, what we are trying to do is basically we are capturing the socio-demographics of the user at the time of registration, and then we are taking some vehicle details that the user is driving, and the details such as motor tax. And we are also capturing the likelihood, to switch to an EV, the preconceived notion that we call from the user. That's all. That's what the user has to do. After that, everything is done in the background. We are fetching a lot of variables within the app, such as the user's driving distance is automatically fetched, by the app, and we are continuously updating the rates of fuel, such as that of petrol and diesel. We are taking the consumption values from motor tax document and also the emission factors from there. And after that, what we're doing in the background is we're calculating the costs, the weekly costs as well as annual costs. And in weekly costs, we're only considering the running cost. In annual cost, we're considering running costs, maintenance cost, and the other costs as well. And we have taken measures that we relate it in such a way that it is very much related to the real world scenarios. Sorry. And after that, once the costs are calculated, they are compared with a standard EV. And in standard EV, we are not considering zero emissions for that EV, because we know that life cycle. If we talk about the life cycle of an EV, there are some kind of emissions. So we have considered those emission values as well. And then the two scenarios that we are considering are, the first is if the person who is driving a car, if he is using public charging, then what would be his cost savings on weekly and annual basis, and what would be the emission savings on weekly and annual basis. And same, the other scenario we are doing for the domestic charging. What if the person is using domestic chargers? So the whole information is displayed on the user's app, and then we are trying to capture whether the behavior, whether the perception towards an EV has changed or not. So the app looks like this on the right, and this is the screen. Is very simple. We have tried to make it as simple as possible so that there are no issues with the user. So it will not interfere much. It will just nudge you after every week and ask you if this information that we are providing you is actually helping you to think positive about EV or not. That's where we are trying to capture. And we are also recommending the range that would suffice the user's needs. And all these values are tailored to the user's needs. So that means every user will have different kind of information displayed on their screens when they're using the app. Talking about the app, we are targeting 5 use cases, and most of these have been reported as very less. They have been they have shown very less uptake of the EVs. Say, for example, a rural population and those without driveways. So we are focusing on all these use cases as well. So far, some really interesting insights, including 1,100 downloads so far, and 1.47 million kilometers have been driven on the app. And we have observed a good amount of savings as well. I think the numbers have not been updated from my previous slide, but it's okay. We have seen that the domestic it's around 600 something, and again there is I think these are the old slides that have been used. It's 84.23 tons carbon. 84.23 tons of carbon dioxide reductions. That we have seen. And if you see on the graph on the right side below, what we have seen is that it has actually influenced the people. The people, once they're given information, they're actually thinking positive about the EVs. Talking about the policy perspectives, I will just come to the future directions because I have very less time left. So we need to optimize EV adoption through evidence-based solutions. That's very important. And then we need to see that we shift towards cleaner transportation systems. And then if I talk about the sustainability pyramid, Electric car it's not on the top. So we need to look for intermodal solutions, taking all the aspects into consideration. And of course, we need to think about sustainable energy and sustainable transportation in a larger picture. Thank you so much.
Thank you very much, Yuba. That was really interesting. And that app looks very attractive, like very usable. So well done on all the work on that.
Thank you.
We're going to move to questions and answers. And just if anybody does have any questions that they would like to put to the panel, please send them through. I have a couple here directed at Niamh first. So Niamh, you're in the hot seat. And the first question is, the questioner is saying that one of the challenges for appraising district heating networks is how to capture the qualitative benefits. So things like contributing to heat targets and the climate action plan and the red directive. And really their question is asking, does the research that you're doing or that you're looking at do that for Ireland? Is there, are people looking, I suppose, at the qualitative benefits?
Yeah, that's a really, really good question. And it's definitely where I would say the cutting edge, I suppose, in this research is and for renewable energy projects across the board, I would say it's not just in terms of district heating, is how to put a value on the attainment of reaching our targets as opposed to something just making monetary sense, for example. So I suppose one of the advantages, I suppose, by doing a project like this is that we have now outlined the kind of criteria and the approach and the assess, how somebody should go around collecting data for a project, for example. And the follow-on step will now be how, I suppose, some of that data is then critically assessed. For example, if there's to be a funding stream in the future, what kind of value will you put on those it's kind of socioeconomic benefits, really, and the carbon abatement. And I suppose district heating, by its very nature, lends itself to contributing at scale to both local and national targets. So we do have to kind of take a national approach to that, and definitely it's a great question, and it's something that we're actively looking at. Thanks.
Very good. I actually have a second question for you, Niamh, so you're back in the hot seat. So one of the questioners has said, thanks very much for outlining the district heating feasibility template, and they're wondering, will that include guidance or information on recommended decarbonised heat sources for district heating in each location? Or is it based solely on kind of the pipeline of planning at this stage?
No, that's a great question, and certainly this is where a lot of the challenge was as well, in terms of developing this template, is identifying that each district heating project is unique. Just as every town and city or locality or area is unique, and that you would need to look at the local heat demand, and then also you need to look at what heat sources will be available locally. And certainly it offers guidance, I suppose, on how to independently assess and compare different heat sources, and it would offer, say, going through a long list criteria then into short list, and you'd be looking at the proximity, the temperature, the cost, the scalability, the stability. It's all of those kind of parameters that you need to look at, and then as you step through the process, that you would arrive at a preferred technical and economic solution for a district heating scheme. So it's very much meant to be guidance on how to independently screen and assess heat sources for each individual project.
Great, that's really good, Niamh. Thanks very much. I actually have a question myself for Sophia, if that's okay. Sophia, I was just wondering, you spoke about the kind of digestate that farmers are using, the kind of improvements, and I was just wondering in terms of how farmers have reacted to using digestate. Like, is it something that they're very accepting of, or are there concerns around it? Or just wondering if you've come across information around that.
Yeah, thanks for the question. Yeah, so there has been skepticism around AD in general, but I think in terms of the digestate, as they know that this digestate will come mainly from grass silage and slurry production, which is sole agricultural feedstock, and it's been proved that digestate has a lot of N, P, and K, even more than slurry, which is the conventional application. I think they're more than willing to accept that. I mean, it's as part of the supply chain, like they providing feedstock and being returned with digestate, it makes sense to the cycle that I was mentioning. But yeah, there's been quite a skepticism, but I think when research outputs come and like industry start to take initiatives and stuff, and they actually know what's going on, I think their skepticism will reduce, and certainly they will be more than willing to participate, or at least we should stay positive that it would be this way.
Very good. Thanks very much, Sophia. Just a question to James as well, just around, you'd mentioned, that the work that you're doing is like an early warning system for energy poverty. And I suppose it's, how can that be translated into action then?
Yeah, so I suppose what we're doing is being able to identify homes that are, or identifying risk drivers of energy poverty, and identifying, the homes that would benefit the most from an upgrade. So I suppose, using the software, what we'll be able to do is recommend what, home upgrades houses will be able to get in order to get the most benefit. So, for example, houses, they might improve their energy efficiency greatly just by, getting triple glazed windows or double glazed windows, or getting, cavity wall insulation or something like that. So we'll be able to kind of determine what measures can be applied to what houses in order to kind of get the maximum improvement in energy efficiency in the residential housing portfolio. And hopefully the knock-on effect of that will be that people will be spending less on their energy bills, because, they're not spending a huge amount of money to heat a very energy inefficient house. And then ultimately, they'll kind of reduce their spend on energy, and potentially overall reduce the level of energy poverty in the country.
Very good, James. Thanks very much. And Tudor, just a question for you. In terms of sort of what would you say is kind of the biggest contribution that sort of local energy markets can make in terms of sort of our vision for 2050? Like, is that the way you see it going in the next number of years, that we'll see more kind of sharing of electricity and energy markets?
Yes, I think that this is a path that every country will follow. We need to, but there are some relevant issues here, because the most important are the grids. The grids are owned by grid operators, and they are not so willing to give to the people access, or to give them for free the opportunity to use it. So those local energy market need to, as I said, we are trying to put together in this project all the stakeholders, and we are trying, in fact, to incentivize them to participate by providing a dedicated business model for each. It will be on the platform. We will have a dedicated business model for each type of stakeholder, and we hope that this will become attractive for everyone. As I said, now it is quite difficult. It is much easier to generate. It seems like it's much easier to generate energy, renewable energy, than to store it, and by that to optimize the generation and the usage. So yeah, this is the future, but we need to define by policies, of course, and different other initiatives, including technical innovation. We need to define the exact steps and try to be as inclusive as possible.
That's great. Thanks very much. And I have a question for Ubad as well. The question that's come in is, on the Tracked EV app, what channels are being used to advertise the app's potential to users, or the app's to potential users?
Yeah, we have a big plan. So we've already done it. It was, I think, published on the national newspaper as well. And then it was done, the advertisements were done on the TCD, social media platforms. And we also are planning, there are some events coming. SEAI has some events coming up in October. We are trying to push our app through those channels as well. And apart from that, the registrations usually go up in the month of January. So we're also trying to promote the app before that, because you will see a peak in the graph of sales, car sales in the month of January. So we will also try to promote our before that in the month of December. So we're trying to promote it as much as we can, because our target is 10,000 users. So we have it's a long way to go.
And well, it's definitely sparked interest here, because I've received another question, and it's, can you suggest whether the app is still live and where to download it? And are you still looking for more people? So it sounds like you are. So that's good. If you can let people know where they can download it.
Yeah, it's available on the Track EV website. They can email me on my email ID. I can share the links, but it's readily available on the Track EV website. We have QR codes everywhere on there, and there are videos as well. So just type in Track EV app in the research, or you can just directly go to your Play Store or Android store, the iStore, and you can just type in Track EV research app, and you should be able to get it.
That's great. Thank you very much, Ubad. And I'd just like to thank all of the speakers. That was a really good session. So thanks to Niamh, Sophia, James, Tudor, and Ubad for really great presentations. And thanks to everybody that sent in questions. And so this is really the end of the research sprint. So thanks very much to everybody for coming. We'll be going to a break shortly, but I'd just like to recommend people, if they can log out of this session and log into session 3. The session 3 is going to be very interesting. We have Jim Shear from SEAI who's chairing it. And we're going to have a keynote speech from Una Buckley, and then we're going to have a very interesting panel session. So if you can log out of this session and log into session 3, that would be great, and enjoy your break. And thanks very much, everybody. Thank you.